All right, as a general rule, I hope that I don't have many canceled classes this semester. As some of you probably well know, last semester I had my stroke in April, which meant that I wasn't at work for about a month and then I'm still technically on MC. My MC runs through the end of October, and actually the doctor wanted to put me on MC till the end of the year. And the reason I'm on quote MC and I don't turn it in the UniKey also. I have the letter with me from the doctor saying that, I'm not supposed to be to work because I have very low energy. I drive to work. I just started driving last week, by the way. My stroke was in April, and I was not able to drive till about a week ago. And I got to driving. I had to force myself to drive because of my wife's surgery coming up. One of us has to drive, otherwise we don't eat. Because neither of us have a lot of energy to cook right there. So I come to class at like an hour or two before class, get ready for class, and then I leave shortly thereafter. I'm not here a lot between classes right there. And Dr. Tyrell is very generous. He only gave me one class this semester, although it looks like I'll get a second class coming up so I don't have it very tough. And the reason is also so that I can concentrate on my occupational and physical therapy right there. So some of you probably have had uncles, aunts, parents have had strokes right there, and you know that you don't recover from them in 2 weeks, right? I've ran across people that have been years trying to recover from strokes. Some people that are not able to walk I know one guy at the mosque I go to on Fridays and his stroke was 7 years ago, and he's still in a wheelchair. He's about finally ready to graduate to using a cane. So it took him 7 years. The fact that I'm able to walk after 3 or 4 months is actually somewhat of a miracle in terms of stroke recovery. All right, I'm recording this now as the recording is started. Soon to be recording right there. Okay. Again, I'm going to kind of go through a set of slides. It's kind of an introduction to industrial robots. Last week I put up a video. We talked a little bit about the video about where robotic research is going. Last week's video that I put up, and it's still there. I want you to watch it, and I'll probably come up with an assignment between now and Thursday, and I'll post, where I want you to kind of answer some questions about the video right there. It's not going to be worth a lot towards your grade, but just mainly to see that you watch it and kind of provoke some thoughts about it. So, and the reason I had that video is I wanted to show you the direction where things are going and how complex videos are. This particular set of slides is kind of talking a little bit more about the history and where robotics is at today from an industrial standpoint. Most of you, and not everyone in this class will deal with robotics. If you graduate and you go to work for a company that builds buildings and you're doing wiring for the building and specifying how many, what gauge wire goes into what room, how many lights you need in a room, you won't deal with robotics. If you go to work for, say, I don't know, the LRT company, I don't know, what is it? Rapid KL, right there, and you're working for them maintaining, the ERL or the MRT or LRT or whatever it's called this week. I guess one's called the MRT and the other is called the LRT, right? That's there. I always got them confused because you got the monorail, you got the MRT and the LRT. And if you're working as an electrical engineer and maintaining and upgrading and those facilities, you're probably not going to work with robotics. If you go to work for Proton or whoever Proton becomes known by I know that they recently sold, I think they only sold 49% of the company. yeah. So 51% is still owned by the government-linked company that's there. So, but so I assume the name Proton will still be around for a while. But if you go to work for them manufacturing automobiles, then you very well might likely see robotics of some type in an industrial standpoint. So I can't predict, looking around this room, that you're not going to see robots, but you are. You know, I'm just picking on you two in the front because you're close out there. But I can't predict who's going to see robots, you know, in their career. And you may not see robots at your first position, but you know, later on, they become, you know, one of the things some of you might end up going to work for is Petronas or one of their supplying companies that do offshore drilling. Today, they don't use robotics so much, but you might see some underwater robots down there doing welding and repairs of oil rigs. You know, a friend of mine graduated, he didn't go to college. Well, he did it later. You know, he's got a bachelor's degree now, but at the time he went to scuba diving school when he finished high school, then went to work off of the coast of Brunei, lived in Singapore, but worked off the coast of Brunei doing underwater drilling for oil rigs out there. Very dangerous work out there. I mean, he made a lot of money doing it back then out there, but he did that for a number of years, and obviously that's a high-paid occupation. That's very dangerous. It takes somebody with a little bit of brain damage. I hope he doesn't watch this video, but if he does, it's okay. I mean, that's there. You know, everybody knows I've got brain damage now. I've got the MRI to prove it. That there. I mean, that's what a stroke is actually. Everyone jokes about brain damage, but that's what a stroke is. It's a dead part of your brain. That there. But regardless, that type of work may very well find itself replaced with robotics right there. So, okay, let me kind of go through and slideshow from the beginning, right there, and kind of talk about this. This is from a book that we're not using that there, and this is for a course that we're not teaching, JV 505, Industrial Robotics and Automation. It happens to have the same title as this course, so the slides are proper, are good to steal, right? Right there. And as I mentioned before, I used to worry about stealing people's slides, so I found all my slides have been stolen. Right there. So that's it. Okay, the learning outcomes for this chapter, and this is kind of the same. I will try to find the book, but I will put up some links to some books that are profitable, or at least some good references. But we're going to define what robotic automation is, the advantages and disadvantages, the 6 types, and explain robots automation in production. These are 4 things that kind of cover the first few weeks of this course right there. And and one of the final exam questions, I will tell you right off the bat that during the course of the semester, I will point out that last semester and the semester before, one of the questions on the final exam is state the advantages of using robotics in industrial applications. So, so right off the bat from this first set of slides is one of the answers to one of the final exam questions right there. Now, I'll review all these comments just before the final exam, but I'm just saying that that at least 1 out of the 5 final exam questions, a lot of it comes from this first set of slides that I'm going through right there. So, okay, contents, this just kind of repeats the same thing. Okay, what is a robot? And I'm not going to read these to you, but I'm going to explain them. It's a machine that can be programmed to provide a variety of tasks. In other words, it's a mechanical machine that's normally computer controlled. Not necessarily computer controlled, but normally computer controlled, that performs a task or a variety of tasks. Now, normally for something to be called a robot, it can't perform just one task, but multiple tasks. It can be reprogrammed to do different things. Now, the robots that were talked about last week in that video, you know, some of those were learning robots that are being taught how to teach themselves. As a general rule, 99% of the robots today that are outside the research circle right there are robots that are programmed to perform a task or multiple tasks by a programmer there. Now, robots are designed and built by companies that build and design robots. I suspect that none of you will probably work for companies that design and build robots, but I could be wrong right there. You know, I used to say that back in the U.S., and come and behold, General Motors, a company that some of you have heard of, and I'll talk about them in more detail. They opened a factory in the city that, you know, Fort Wayne, Indiana, where, you know, the city that I was living in, and they actually had some engineers that graduated from our program design robots at there. So, you know, I used to think that robots would never be designed and built by at there. And I really haven't, this is actually not a course at my previous campus. We did not have this course, but we did include robotics and factory automation in some of our courses. So, right there. There's three laws of robots. The video kind of alluded to them. They did not give those, but the three laws of robotics are: a robot may not injure a human being, or through interaction allow a human being to come to harm. Now, that's a major tenet of robotics. These were came up with before robots were actually built. That's a major law of robotics when we start looking at robotic-driven cars, vehicles. So what if a vehicle is given a choice of hitting a pedestrian or going off a bridge and killing the driver of the car? I mean, that's a very tough decision for you as a driver to make. You know, if the pedestrian on the road happens to be a mother pushing a pram and carrying a baby, you may opt to go ahead and drive off the bridge that there. But if it happens to be, you know, some guy staggering carrying a bottle of whiskey, you may not care so much whether or not you hit the guy. You know, your life suddenly becomes more important. What if your vehicle contains your wife and 3 children? There. Now you've got this. Now the choice is between you and these are ethical questions. That there. And the latter part of that video that I posted last week starts talking about some of these ethical questions right there. Is that the law of robotics says the robot may not injure a human being or through inaction allow a human being to come to harm. Well, as soon as you put robots into vehicles as driving at there, you know, now the robot is in a situation where it may have to make a decision. What about robotic drones? And I'll pick on my country, you know, my place of birth. I don't live there anymore. But the United States is quite famous at building robotic drones that hold their entire purpose is to go out, seek people, and kill them. You know, military drones. And you hear about these all the time. But these are robots, essentially. Again, it's a machine that can perform a variety of tasks. In this particular case, it's a machine that's designed to fly around. It has a GPS built into it, so it knows where it's at. It's got cameras so it can see. It's being controlled by an operator on the ground. And the purpose of the robot is to kill. Now, it just so happens that the U.S. military, and this is what I've been told looking at their battlefield management systems and some of the companies that build these drones, you know, and I've visited companies that build drones. ITT Aerospace, has a plant in Fort Wayne. It's called Galalis now. Raytheon has a research center in the city. So I'm familiar with military research, military. And that's the area I worked at before I started teaching. I'll admit to that. I worked on things for the military out there. So I worked on systems that hunted submarines. I looked at systems that were guns that shoot tanks, things like that. So I've worked on some of those systems in the past. The U.S. military has a policy that a robot is never left to make that decision. So there's a human operator at the end of the drone that says fire or no fire. So in a way, they get around this law of robotics because the robot doesn't make the decision. The decision is being made by a human operator sitting, 500 miles, 3,000 miles away. We don't know how far it is, but these decisions are being made by human operators. They're not, in other words, the drone isn't turn loose and say, go out and look for bad guys and whoever you have to find, shoot. That they happen to be controlled. But again, we are using robotics in the killing of individuals. Malaysia isn't, as far as I know right now. I should stick that out there. There's probably lots of things I don't know in the world right there. Russia probably is. China's probably working on such technology. Israel, I know it has been working on such technology. Matter of fact, the first military drone was an Israeli product. It wasn't the U.S. military that designed the first military drone, it was actually Israel. Okay, rule number 2, robots must obey the order given to it by human beings, except when such an order would conflict with the first law. Well, we've already talked about in great detail that we give robots the order to kill, which violates the first law. So law number 2 is actually violated on a regular basis, right there. So that there. And law number 3, the robot must protect its own existence as long as such protection doesn't conflict with first and second law. In other words, the robot shouldn't self-destruct, unless, of course, the only way that it cannot do 1 and 2 is by self-destruction. So robots are designed to self-preserve just as human life is designed to. The Quran is very clear that taking our own lives is haram, right? Suicide is haram. The Christian religion has the same rules. The Jewish religion has the same rules. In other words, suicide is not an option. However, there are times that, as I said, driving your car off the bridge to save a family of 3 and you're by yourself, is a difficult decision. And sometimes, that's the decision you make, not because you want to commit suicide, but because your death is not as important as up there. When you look at value of human life, somebody who's 60 years old, whose kids are raised, and has nobody depending on them for survival, maybe my life is more expendable than the 22-year-old with 3 children. Those are really tough decisions. Okay. Now, we're getting into the 5 parts of robotics, and this is where my use of my hand becomes interesting. First, we have the controller. Oh, that's right. This thing here doesn't. I had that problem with one of my other classes last semester, that this pen doesn't work with some of these projectors. I think the mouse doesn't it? Nope. Okay. Well, we'll just use the mouse and point to it right there. The controller is typically the computer system that drives the robot. And it can be as elaborate as a very large mainframe computer with multiple microprocessors, and maybe even there. Some of the early robots had very elaborate. Or it could be as simple as a 8051 microcontroller right there. Raspberry Pis are becoming popular for small robotics. Right? But the controller is typically some type of microprocessor / computer controller right there. The manipulator, and these kind of get a little bit, see, that's the arm, your shoulder right there, right there. That's the arm right there. That's what you manipulate in order to get the end effectors in position. In the case of my arm, and mine doesn't work very well right now because my controller is damaged, but is my hand right there. That's my end effector. That's what picks up this mouse. That's what enables me to write. Right there. My arm actually works pretty good. It's my fingers that are numb. So that's what makes writing very difficult there. Actually, my arm didn't work at first. It's actually being reprogrammed, but we'll talk about that here. So the manipulator is what actually that there. The actuator is what controls the manipulator. So when we look at the human being, and we'll just use myself as an example, my controller is my brain, right there. That's what controls what I'm trying to do. My manipulator is my arm, right there. The actuator happens to be the muscles in my shoulder and in my arm and in my elbow, or there, that will control. Now I have joints, like my elbow is a joint, right there. But the elbow itself is not a manipulator because the muscles, if I want to pick up something, my bicep is what picks it up. If I want to move this way, the tricep moves that. So I have two muscles, tricep and bicep, right there. And this isn't, of course, in anatomy. I won't ask the question, but bodybuilders are quite familiar with trying to make their biceps look bigger. I mean, that's how, bodybuilders try to impress the girls with great big, huge arms. These aren't so huge, that there. Back when I was younger, I used to go to the gym and sit there and do curls to make my biceps bigger. That way I can pick up more weight, right there. So your manipulator is the arm itself, and the actuator is the muscles that move that. Now, when we look at robots, our actuators are most likely not going to be human muscles, but they're going to be motors, they're going to be hydraulic pumps, they're going to be some type of, something that will move, that the manipulator that there actually is, the end actuator again is the hand. When we look at a robot, the end effector might be something such as a drill bit. We may be drilling holes into an object. So, the robot may bring down a disc for a disc brake that goes on a car, and the robotic arm comes down and it drills a hole, and then it puts in a tap in order to put the bolt holes to hold the there. Sensors are used to help the robot tell where it's at. So if we look at the human body, our most common sensor is our eyes. We also have our ears. Now we can measure distance because we've got bifocal, vision that can then, that can kind of narrow down, and I can tell that these two ladies are closer than these five guys who are in the back, right there. And my brain makes that decision based on the angle in which this eye sees her face and this eye sees her face, and it kind of pins into where, where that person is. And some people are better at judging distance than others. Now, of course, that whole process is being done inside the brain, right there. But a professional golfer, for example, can look at it, look at the, the flag on a golf course. They tell that that's 220 meters from where they're teed from. Up there. I can look at a flag from a golf course and I have no clue how far it is. I'm not very good at golf. But somebody who's a professional golfer becomes very adept at making distance judgments using their eyes and what information they have available. So their sensors aren't necessarily better. That doesn't mean their eyes are better, but the processing in their brain on how to measure distance is very good. A professional sniper is extremely adept at telling that a target is 430 meters away and the wind is going so far and they have to make a judgment. These are all things that people do on a daily basis. They don't realize what they're doing right there. So when we look at robotics, we have to design systems that can make these judgments right there. So the controller connected to the computer functions the screen, can be networked to other systems right there. If you're designing, for example, a robot on a conveyor belt, it has to be interfaced to the conveyor belt itself, it has to be interfaced to a controller, maybe some cameras up there. So robots have controllers that are run by a programmed set of instruction code. In other words, somebody has to write the code. Now, I don't know how long I'm going to talk today. I've talked about 45 minutes, so I've got plenty of time to talk. But this slide actually is a little bit wrong incorrect, is that quite often we write code to control robots that have what they call a teaching mode. So in other words, I can sit with a programmer and I can tell the robot what to do. And it will remember those instructions and institute the instructions as we go along. Now, one of the things that is fairly common is that there's robots that, and again, the video showed one where the operator actually wore a suit with hand grips and the robot followed through what they were doing. Now there are robots, that's how you program them, is you wear the suit, you show the robot what to do, and it remembers the steps right there. So, but again, the controller is the computer that essentially tells the robot what it does. It's the brain of the robot. Manipulator, this is the arm right there, and again it comes in all shapes and sizes right there. Again, a simple arm is one that has maybe 2 or 3 joints right there. The simplest arm is one that just goes up, over, and down right there. That's a very simple manipulator. We're going to look at all kinds of things. Many resemble the human arm. You saw those last week right there. And again, this places the end effector and the sensors. The manipulator itself doesn't do any work. All it does is bring my hand over. If I took my hand off, let's not remove my hand. It's bad enough that it doesn't work very well right there. It's actually just starting to work in the last few weeks that I can actually pick things up. And every now and then it quits and I drop things. So my wife doesn't let me carry anything valuable. I've dropped more things than I care to mention. Usually I get my foot under it before it hits the floor and breaks. But regardless, right there. But without the hand, moving my arm actually doesn't do any good. Well, if I want to reach down and pick up my pillow that's fallen on the floor in the middle of the night, and my hand isn't working, I can't pick up the pillow. And trust me, that happens to me more than once, where I have to get out of bed and use the other hand to pick up. So, again, having had a stroke, I could talk a little bit more about these and give, not good examples, but examples that mean something to me, right there. So say again, that there? 3 degrees of freedom means that, for example, this is 1 degree of freedom. The shoulder is a rotating, it has infinite degrees of freedom. But let's say I have a shoulder that can move this way only, up and down. That's 1 degree of freedom. Then the elbow moves this way. So now I've got 2 degrees. Then I've got the wrist that provides a 3rd degree of freedom. 3 joints, yeah. And each joint can only make 1 movement. And so like the elbow, you can't rotate the elbow. Well, you can do it to a degree, but not very much. You rotate the elbow too much and it breaks. I know that the knee, for example, has 1 degree of freedom. And if you try to rotate it, bad things happen, because I snapped an ACL one time trying to rotate it. The knee only goes in and out. When I stand here and I move my knee in and out right there, if I put my knee and plant it and I rotate my body, the knee breaks. Actually, the tendon between the knee and the holds together breaks. So, but that's 1 degree of freedom. The hip provides 1 degree of freedom here and 1 degree of freedom here, but the hip is a rotating device, so that's infinite back there. So when we talk about degrees of freedom, we're talking how many different ways can we move. And this makes more sense when I bring in the physical robot that we've got here, and you'll see that it's got 6 motors, so it's got 6 degrees of freedom. Right there. So a simple robot can move up, down, left, right, forward, and backwards. Right there. So that's what we mean by 3 degrees of freedom. And as you recall in the video last week, they talked about some of these robots, and they talk like 20 degrees of freedom, 27 degrees of freedom, 15 degrees of freedom. That means that there's 20 different ways that you can move that robot around. Now, again, not every joint is going to have all 20 degrees of freedom. Again, you look at something like your finger, it actually has 1, 2, 3. A single finger has 3, and then actually 4 to move 4 and 5. A finger has a lot of degrees of freedom. Not there. So, yeah. And that's why, again, when you talk about somebody that, if you look at, of everything on the human body, the one thing that has the most degrees of freedom is the hand. The hand has many, many degrees of freedom. And that's why after a stroke, for example, in my case, it takes so long for the hand to recover, because there's so many different muscles in the hand, because all the multiple degrees of freedom and the number of nerve endings to control them, that have to be reprogrammed. Because what happens with a stroke recovery, and the same thing happens with repairing a robot, is that the controller is damaged. It just so happens the human brain will reprogram the controller if you test it, if you give it enough input and enough training exercise. It's kind of like the 3-year-old relearning how to walk again, or learning to write. I'm like a 3-year-old. I practice writing. I write the letter A 100 times, and I write the letter B 100 times. And literally, that's what I do to get my writing skills back. Is that I'm back to what you would do at grade school. I'm reprogramming parts of the brain to write again, just like I did back in grade school, but I'm programming a different part of the brain. If you have a robot that is damaged, then you have to reprogram it to work around the damage. Right there. So, but the manipulator is the arms, or the legs, or whatever. So here we're talking, this is a drawing. Here's a sweep, that's 1 degree of freedom. Shoulder swivel, that's another degree. Elbow extension. The pitch, right there, this is kind of going like this. The yaw is turning this way, the roll, I guess, right there. So you've got the various degrees of freedom right there. The actuator is a mechanism to allow it to move. Again, we talked a little bit about that. These are the pneumatic and hydraulic cylinders or electric motors. We'll look at a number of these. We're not going to get into the real deep design right there. We could do an entire course on just putting together robots and trying to program that there. And in a way, that's kind of what this course is supposed to be, but I've come to the conclusion that it's not something that's going to be useful to most of you. So I'm kind of going away from, the idea of what's, what are you going to be doing, in industry. I've already mentioned some of you will probably never see a robot, and some of you will be seeing them on a daily basis. But there are those who are going to see them on a daily basis. What job functions are you going to be doing? And you're not going to be building and designing the robot, not at this stage. You're going to be looking at the application. You're going to decide from a catalog or from talking to various vendors what robots you need to buy, and then how to get it, install it. And again, you probably would be paying someone from Toshiba or Mitsubishi or whoever you're buying a robot for. In Asia, it'd probably be one of those two, but the Japanese seem to dominate the robot industry here. There are others. In Germany, there are several companies that build. There actually isn't that many American companies that build robots. Robots in the U.S. are not really. They tend to buy the Japanese ones or the European ones. Actually, Sweden tends to build a number of robots. Okay. Robot position depends on a combination. Now, this is where things get very, very complex with robots, is that if I want to pick up this pen, I can pick up this pen by shifting my body forward, by turning my elbow more. I could bring it over. There's probably an infinite number of ways of picking up this pen right there. So the same thing as robot position depends on the combination of all the various components. So if you look at the textbook that was originally designed to be used for this course, I don't use that textbook, he has a lot of four-dimensional matrices right there. Every place in space can be defined by an XY coordinates, XYZ coordinates right there. And how we get there, we would turn each of our various actuators to a certain position. And there's an infinite way of doing that. And there's a number of matrices we could come up with of how we would set all the various angles of our actuators to reach a particular point, and then how we would need to change them to reach this point, and what's the most efficient way of getting there. And then what's the most efficient way of getting there by going around an obstacle. There's a lot of that type of mathematics involved in moving actuators around. I'm going to skip all that mathematics. One is none of you will probably ever use it. Probably none, I would say very high probability none of you would ever use it. A much even higher probability that everybody in this room would understand that level of matrix mathematics. Even Dr. Saswana would love to say that you could. I tend to doubt that you would be able to fully grasp that, and you surely won't enjoy it, and it would take away from the beauty of what robotics is supposed to be. I mean, this becomes a very dreadful dry course when I start getting in that level right there. I have used robots for fun. I built a little Heathkit robot back in the 1980s, and went around programming it, played with it, took it to some of the high schools for shows, taught a bunch of high school teachers how to build the robot out there back in the 80s. So I went there, and those were relatively simple robots. Those used an old Z80 processor back then, right? Out there, and we had a little hand module for programming, right there. I've worked with companies that have put in robots. I have never been on a robotic project itself. I've never bought a robot and installed it, but I've worked for companies and I've seen them in operation, and I've been allowed to play with them. I've had a number of students over the years as part of their senior design with industry install robotic systems and work with robotic systems. So I've been around them a lot. I'm not an expert on robots. I hate to tell you this, but we don't have an expert in robotics in the department. I'm the closest thing, and I don't call myself an expert in robots. I was actually, someone else taught this course, and they fell totally out of the realm. I'll teach it, but not the way it's supposed to be taught. I'll teach it however I feel like teaching it. So, okay, robotics. But this particular one, again, I can't write here, but if you look right here, depends on a combination of these components. So this gets to be very complex to a degree. And one of your first labs is to figure out how to pick up something and move it. And you're going to do that with trial and error. So the robot has a simple movement that's driven by a mechanical system that uses a cam, and I'm not sure if this idea of a cam, but it's a mechanical system that has a motor or a gear that will move the arm, or it can just actually, if the motor, our robot that we purchased, a number of robots that we'll be using for a few labs here, they actually have very small servo motors in them, and we just tell them what angle they want to be placed at, and the motor itself drives the arm out there. Also, another motor opens and closes the gripper. You know, that we'll talk about the end actuator right there. But again, these actuators don't have any kind of cam or anything. Now, unfortunately, because these robots use a servo motor directly without any gearing mechanism and without any kind of hydraulics or anything, they're very limited in what type of weight they can pick up and carry. I could not pick up a 3-pound book with, or a 2-kilo bag of rice or something like that. It won't pick up that much. It might pick up this mouse right there. So, and here this is just showing with the actuator, and this is just showing a gear right there. So the end vector is connected to the robotic arm right there. The end effector is what does the actual work. It can be a gripper, it can be a vacuum pump, a hook, a scoop, all kinds of different things. I was talking to an individual that works for Intel. He was actually teaching a workshop. They had a problem at work where their robotic was a very small vacuum that picked up an IC and moved it to another place, and then was supposed to release the IC out there. And the purpose was to pick up this little tiny piece of silicon that contained a microprocessor on it and put it inside the plastic packaging so that the wire bonds could be mounted to it right there. So again, this particular case, that was a very small vacuum that picked it up. Now, the robot we have has a gripper that opens and closes right there. Some robots have a hook to pick up an object, an engine, and move it and put it back in place. So a scoop, where it can scoop up a whole bunch of biscuits to put into a bag right there. So these can be all kinds of things. The human body, our hand is the most common one. Our foot is another end actuator, but it actually does very little. All it does is balance the body as we walk right there. So robots can have more than one arm right there. So you can have a robot that picks up an object, another robot that drills into it right there. So, but again, this is, I'm probably going to wrap up with this discussion right here. These are the major parts of the robots up there. Because the next thing we're going to talk about is the sensors, and I want to talk about sensors in its own lecture, because sensors becomes an entire array of different forms of electronics, and we'll spend some time on sensors right there. And there's a number of final exam questions on the different types of sensors out there. So with that said, I'm going to 45 minutes and